Okay, now earlier in the lesson before this, in the first lesson, actually, I mentioned to you that when you're talking about oscillations, oscillation in its simplest form is just repeated back and forth motion on either side of an equilibrium position. Okay, then after that, subsequently, I mentioned to you that when it comes to oscillation, there is a very special kind of oscillation called simple harmonic motion, defined by A equals to negative omega square x, where I say to you that A is always directly proportional to x, and A and x are always in opposite direction. This is what I went through with you for simple harmonic motion. Simple harmonic motion is oscillation, but is a very specific kind, which must follow these two criteria. Okay. Now, for oscillations also, you can also sometimes group it into two different types. The first one is called free oscillation. Okay. Now, for free oscillation is a system that will oscillate after being given an initial disturbance. Okay. So if you have a system, you give it an initial disturbance and it oscillates, it's called free oscillation system. An example of a free oscillating system would be the ones that are shown in the diagram there. Your pendulum board is a free oscillating system because you understand that if you displace it towards the side and release it, the pendulum board will oscillate by itself, isn't it? When you displace it to the side, that is called your initial disturbance. When you release it, there's no longer an initial disturbance there. Your pendulum board will just oscillate left and right, isn't it? That is free oscillation. Now, the same could also be said for your mass spring system. Okay, so if you want to cause the mass to oscillate, you could probably displace it downwards and then you release it. So when you displace it downward and then you release it, your mass again oscillates up and down, right? So when you displace it downward, that one was also called your initial disturbance. But once you release your mass, there's no longer an initial disturbance, your system starts to oscillate by itself. So for free oscillation, you really only need an initial disturbance. You don't need to continuously apply a periodic force to maintain the oscillation. Now, when we say periodic external force, the term periodic here means at regular time intervals. Maybe every 1 second, every 2 seconds, every 3 seconds, every 5 seconds, or so on. That's what we mean by periodic. You apply every few seconds or so, or every few specified time. So in your case, for free oscillation, you don't really need to apply a periodic force in order to cause your oscillation to continue. Just give it an initial disturbance and it will just oscillate by itself. Now, when you have an object that experiences free oscillation, you know that it has a certain period tied to it. That will also mean that it has a certain frequency tied to it also, right? Now, for any objects that are experiencing free oscillations, they will always oscillate at what we call their natural frequency. Any free oscillation system, the moment it oscillates by itself after an initial disturbance, that frequency is called the natural frequency. So there are two different ways in which you can define natural frequency. The easiest definition is where you say natural frequency is the frequency at which a system oscillates after being given an initial disturbance. Or you could also say as the frequency at which an object oscillates when there are no external forces acting on it. Your external force here could be a driving force or it could be a resistive force, which is kind of true. You see, when you say that your natural frequency is the frequency at which your object oscillates when no external force acts on it, you consider this now. Once you give your system an initial disturbance and then you release it, after you release your object, after you release it from the initial disturbance, there's no longer any force and it was oscillating. So it's actually correct to say that your object was oscillating with no external forces acting on it. Now, when it comes to the definition of natural frequency, this one is actually the more common one in your marking scheme. The first one here is actually something that I've never seen before, lah. Okay, but it helps you to understand what natural frequency is. In the event that you're asked to define natural frequency in your exam paper, it will probably be best if you use the second definition. All right. Now, then another thing that I should also mention to you is this. If you give your system a larger initial disturbance, it will tend to give you a larger amplitude of oscillations. It's related to what I just mentioned to you earlier. Just now I mentioned to you that if you give your system some sort of initial displacement, your maximum possible amplitude will never be larger than that, right? So similarly, if you give your system a larger initial disturbance, you're going to end up with a larger amplitude of oscillation. But it does not alter the period and hence frequency of your oscillation. Now, what do I actually mean by that is something like this. If I give you two different pendulum bobs, this one is my first pendulum bob. This one I mentioned to you, I displace it by 5 centimeter. This is my initial displacement. And then I also have that same pendulum bob again. But this time I mentioned to you, I displace it by 10 centimeter. This one I displace it much further, say maybe at 10 centimeter. Okay, this one is displaced, like I said, 10 centimeter as my initial displacement. Okay, so in both cases, after the initial displacement, the moment I release the pendulum bob will just oscillate from left to right. Okay, it will oscillate from left to right. And then after that, they will have their own corresponding value of amplitude. Let's just say this one is your x0, and then this one is your x0 also. So I did mention to you that your maximum possible amplitude will never be more than your initial displacement. So your x0 here will be equal to 5 centimeter or less than that. Okay, this one also same. It will be equal to 10 centimeter or less than that, but never more than the initial displacement. Okay, but what is of interest to you is the period of its oscillation. So while we know that a larger initial disturbance gives you a larger amplitude of oscillation subsequently, what happens to the period and the frequency? This one, you can say that it probably has a period of, say, T1. Maybe I give you a period of, say, 2.5 seconds for this particular case. Even if you were to repeat the same oscillation, you were to repeat the oscillation with the same pendulum bob but with larger initial displacement, your period would actually still be the same at 2.5 seconds. Your T1 will be equals to your T2. Okay, so T remains constant, therefore frequency also remains constant. So although there's a different displacement, different amplitude here, how is it possible that your period can still remain constant? How is it that your frequency can remain constant here? The key takeoff point was that the period will remain constant. That's the reason why your frequency was constant. Okay, but why is it that your frequency is constant here in the first place? Now, for the case of the second oscillation for the same pendulum bob, what we will say here is that the mass moves faster over a larger distance, so that period remains the same. Because you can see that if you are talking about the distance that has to be moved by your mass as it oscillates, the second example here would have a larger distance to cover, right, in order to complete one oscillation. So in order for your period to remain the same here, in order for you to take the same time to complete one oscillation, your mass here has to move faster. So you causing a larger disturbance here causes a larger amplitude, but at the same time, it also causes your mass to move faster so that your period remains the same here. So I actually mentioned this in the notes already. Instead, your oscillating object will move faster so that your period remains the same when you have a larger initial disturbance. This one of the questions later on, you will see this fact being applied. All right. Now, so this is for free oscillation. If we have free oscillation, we also have something called forced oscillation. So what is forced oscillation in the first place? Now, forced oscillation is a type of oscillation in which it must be forced by an external periodic force. Forced oscillation is forced into motion by an external periodic force. So just now I mentioned to you what is the definition of periodic. This one I already mentioned is at regular time intervals. You need to apply a force at regular time intervals every second, every few seconds in order to cause the oscillation to continue. So a continuous force needs to be applied, which also means that a continuous energy input is required for your oscillation to be maintained. And then when your object is undergoing a forced oscillations, the frequency of oscillation is the same as the frequency of your periodic force. Now, what is the example of forced oscillation? An example of forced oscillation could be this. You see, I'm sure right around you right now, you have your stationary, right? So if you look at your ruler, if you take your 15 centimeter or 20 centimeter ruler with your hand, and then you go and wave your hand up and down, you will notice that your ruler will also vibrate up and down as your hand moves up and down, right? So as long as you move your hand up and down, your ruler will also continue to move up and down. It's actually oscillating here. So that's why here I gave you an example. Waving a ruler up and down causes it to oscillate. This is an example of forced oscillation. If you go and move your hand up and down at a certain frequency, say 5 hertz, 5 cycles per second, your ruler will also oscillate at the same frequency at 5 hertz. If you somehow change the frequency of your oscillation, you go and move your hand even faster to say maybe 10 hertz, your ruler is also going to oscillate with that same frequency. So it will also oscillate at 10 hertz. So that's why here we will tell you the frequency of your oscillation for forced oscillation system will always be the same as the frequency of your periodic force. So here you define forcing frequency as the frequency at which an object is made to oscillate. All right. Okay, now there's one very important fact that I need you to know. Now, all objects will have their own natural frequency of vibration, regardless of whether they are free or forced oscillation system. Just now in the previous section, I mentioned to you, when you have a free oscillation system, they oscillate at natural frequency, right? It doesn't mean that forced oscillation does not have natural frequency also. Forced oscillation also has natural frequency. All objects have their own natural frequency of vibration. It's just that natural frequency is readily shown during free oscillation. Natural frequency exists for all systems, regardless of whether they're free or forced. It's just that for free oscillation systems, the natural frequency is readily shown. Your forced oscillation system also has its own natural frequency, just that you don't see it when it is oscillating. So that's just one thing I need you to know, because it ties up to something later on in resonance.